So, ladies and gentlemen, what we see on the board that a vector g has been projected on the x-axis and it is represented as c of x. Now, if we want to express g in terms of x, it is c of x. But what was the actual vector? The actual vector was z. So if we consider in a two dimension, the vector g, when represented in terms of x or in the x direction, there is an error that is g minus cx. This error signal and its energy, you can see from the board also, we have plotted three dotted line, and among these three dotted line, the shortest one is the perpendicular line. Therefore, the error energy, we will, if you calculate the energy of this error signal E, this will be minimum when we plot this when E is, that means E is represented in the direction perpendicular to x-axis or x direction. What does it actually mean? It means we can analyze it in two ways. One is when g is represented in terms of x, the error will be minimum if g is perpendicular to x. Okay, or in other way, we can tell that if we can project or if we can represent this error in the direction perpendicular to x direction, that means we are adding this error, we are adding this cx, vector addition of this error with cx will give me g. We can exactly represent g in two dimensions if the projection on the x-axis and this error are vector summed. And we have calculated and seen that this vector addition will give the value g with minimum error if E is represented in a perpendicular direction to x. That means if we can add this E to this vector g, this is vector g and this is our error signal, error vector here. So if we can plot, consider another direction which is exactly perpendicular to x, and if we vector add these two, then we can get g with minimum error. So this is the basic conception. Likewise, in three dimension, if we go, what will be the happening? So I have already discussed in the signal theory. There will be, we will need three direction or three dimension which are perpendicular to each other. That is, in another term, they are orthogonal. In case of vector, when the two vectors are orthogonal, when the dot products of them, that is this magnitude of this vector, this magnitude of vector into cos theta, and here theta is 90 degree, that means their dot product is 0, then we call them as orthogonal vector space. Orthogonal vectors. Now, we told that signals are nothing but the vectors. Therefore, if it is true, then we can also represent the signals, periodic signals or aperiodic signals in terms of signals which will complete the orthogonal signal space. What is that orthogonal signal space? Therefore, if we see the vector, what we see that if we want to represent a vector in terms of other vectors or in a whatever maybe surface or plane, we must consider the vectors which are perpendicular to each other, and the vector we want to represent should be mapped or projected in the direction of these orthogonal vectors. Likewise, there was the necessity to form the orthogonal signal space where the signals will be considered orthogonal to each other. If we can do that, then we can represent signal in terms of this orthogonal signal space. Now, how this concept of Fourier series and Fourier transform F has already been discussed in signal system, and the history how it was derived through the Eulers, then Bernoulli, and finally shaped by Fourier with the conditions imposed by Dirichlet have already been discussed in the class. We are not going into that part. Rather, here what we are going to think that the importance of orthogonal signal space, which is very much essential to understand the communication engineering. If you can see page 3 of week 1, you can see the condition of orthogonality of two signals. What is that? If x1 t and x2 2, if we multiply these two signals and take the integration over a time period, if it is 0 for m and n not equal, and for m and n equal, if it is equals to t by 2, where t is the time period, then we will call that these two vectors, two signals are orthogonal to each other. Now, after checking this cos n omega 0 t and cos omega 0 t, m omega 0 t, sin n omega 0 t and sin m omega 0 t, cos n omega 0 t and sin m omega 0 t, with different condition of m and n, we see the signals cos m omega 0 t or sin m omega 0 t, whatever we use, notion we use, all these cos and sines, all these sinusoidal signals are orthogonal to each other. Okay. The reason of this condition, that the integration of the area of the integration of the product should be 0 for to be orthogonal, has already been proved. The students can go for any standard book where they can see these conditions, and parallelly it was derived why these are considered as orthogonal signal space. Whatever be that, what we may conclude from here, that if we can represent the signal in terms of other signal, then it is necessary to consider or to represent the signal in terms of signals which are orthogonal to each other or in a orthogonal signal space. Likewise, in a orthogonal vector space in case of vector. Then we found that cos and sine signals, if we multiply them and take their integration in different conditions, they provides the value 0, and for same value of m and n, in case of cos with cos, sine with sine, they give half the time period. Therefore, we have also concluded that cos sine signals are orthogonal to each other. Therefore, the final conclusion was a signal, if we can represent it in terms of infinite number of sine and cosine terms, then the approximation error can be minimized. And we also derived the expression of Fourier series coefficients, and where gt is equals to a0 plus n 1 to infinite an cos n omega 0 t, and bn is 1 by t over the time period gt sine n omega 0 t. And for orthogonal complex signal, for the condition for orthogonality in complex signal, I am telling in this case, that will be gt multiplied g star t, g star 2t should be 0. So what we are telling that how to calculate the coefficient a0, a and bn. The derivation of this has also been done in the class, and this is the trigonometric form, and then the cos and sine, we combine them two and represent it in compact trigonometric form by only the cos terms, which inherently includes sine also. We also expressed Fourier the signals in terms of complex exponents, like gt is cn e to the power j n omega 0 t, n minus infinite to plus infinite. We also derived the relation between different type of representation of Fourier series, where an, bn, cn, an, bn and a0 can be derived from the exponential Fourier series, and also the compact exponents can be derived in the similar way. Then at page number 5, we have considered an example, and we have derived is trigonometric coefficients, then exponential, and then from exponential trigonometry, and finally we have plotted the magnitude and phase of the Fourier series coefficient Cn, that is of exponential Fourier coefficient. We have plotted the magnitude and phase of the exponential Fourier coefficients. Finally, so these all things have been done in the previous class, where what I want to mention to avoid any confusion, ambiguity while studying different books, that you always follow a particular notation for trigonometry, exponential and compact. Likewise, I have used for compact represented by t suffix n, and for exponential it is cn. Some books use the vice versa. If you use it, there is no problem, but you follow it throughout the study. Throughout the study, you follow this notion. Another thing I want to tell you that okay. Here you see the findings will tell later at the final stage. But before that, you see another important findings, very interesting findings to calculate the power of a periodic signal from the Fourier coefficients. That is the if you write the expression of compact Fourier series as d0 plus n1 to infinity t n cos n omega 0 t plus theta, then we see that if you consider two cos signals with different frequency and phase, finally we conclude that the power is nothing but the summation of power of the individual cosinusoidal part, and in another word, it is nothing but the Fourier coefficients dependent expression, that is d1 square by 2 plus d2 square by 2, where d of n is the compact Fourier series coefficients. Here, try to keep in mind that over a time period, either cos or sine signal for a over a time period, this cos omega 1 or omega 2t plus theta 1 or theta 2, if we integrate over a time period, you can easily find that over a time period, whether we integrate a cos sinusoidal signal or a sinusoidal signal, it always gives 0 for the positive side area and the negative side area are same. And if there is term like cos square, try to express it in terms of cos or sine, not cos square. Don't keep cos square, it will be difficult to calculate. Then you follow the basic mathematics. I think you can do it yourself. So here we find an interesting thing, that whenever you are dealing with a very complex periodic signal and you are going to calculate the power of the signal, if you cannot calculate using the formula that power is limit t tends to infinity 1 by t g square t dt dt, then what you can do, you can calculate the Fourier coefficients, and from the Fourier coefficients directly you can get the power of the signal. But here, two things you should always keep in mind. Whatever discussion we have done, or whenever we have used signal, that means to the signals which are periodic in nature. Okay? So, this holds only for the periodic signal, that power of a signal is summation of power of the individual parts. What is that individual parts? Try to confine your or concentrate your very high or with deep thinking, that it is very interesting or important findings that you can only get the power from directly adding the Fourier coefficient or by adding the different signal having different frequency. If we sum them up, then we will get the signal. That means you are representing a signal or decomposing a signal in terms of certain signals. That means, let's consider a signal Gt. You are expressing this in terms of G1t and G2t. If Gt is only periodic and it is it can be expressed in terms of G1 GT T. If we want to calculate the power of GT, it is the power of the G1 T plus power of G2T. That means summation of power of parts of the signal which has combined 3 from GT. This only holds, or this is only true if G1T and G2T are orthogonal to each other. Right? This is another important findings which inspired the Fourier series, that if you can represent a signal in terms of orthogonal signal space only, or orthogonal signals only, then you will get several advantages, including calculating power of the signal. Then we have calculated one thing. Then we have evaluated the Fourier coefficients of a square wave in 2 ways, or in 2 cases. One, when you see carefully this one, okay, I am drawing. You see these 2 signals carefully. What is the difference between G1T and G2T?